Okay, so our next talk is by Ira Gessel, and he's going to talk on an application of the Goulden-Jackson cluster theorem.
Thank you. I'd like to thank the organizers for doing such a great job of organizing this conference. I'm very happy to be here. I first met Ian and David back in the late 1970s. I think when I'm not sure if I was still a grad student or not, but whatever, it was my early days as a combinatorialist. And my thesis was on what we called sequence enumeration. And that's a topic that Ian and David were working on in those days. And they've moved on to other things, whereas I've still been working on the same kinds of things to some extent, and some other things. And one thing what I'm going to talk about today is an application of a really beautiful theorem that Ian and David proved, called the Goulden-Jackson cluster theorem. It's about counting words with forbidden subwords. And for this talk, subwords are always consecutive subwords. So in more recent years, people have been studying what they call permutation patterns, which are subwords that are usually not necessarily consecutive, but they've also looked at consecutive patterns. And in looking at those, the cluster theorem is very useful. And in particular, Sergi Elizalde recently a few years ago, wrote a paper applying this theorem to some problems of consecutive permutation patterns. So what I'm going to talk about is a little bit different. So let's get going. So just some background. We're talking about words in an alphabet that I'll call A. A star is the set of all words. I'm going to take this off. I think it'll be okay. My voice will be a little clearer. So we're looking at the set A star of all words made out of the letters in A, and we multiply them by concatenating them, and we take formal sums of these words, and we get something that we can think of as an algebra of formal power series in non-commuting variables. So we're going to work in this algebra of formal power series in non-commuting variables. The variables are the letters of my alphabet. And I'll write 1 for the empty word, which is the identity element of this algebra. And we'll say that a word is a subword, a word U is a subword of a word V, in which case it occurs somewhere in the middle or possibly at the end. So subwords are always consecutive. And I'll take a set of words that I'm going to call forbidden words. It can be an arbitrary set of words, but they should all have, they should be non-empty. And to make things interesting, they should have length greater than 1, although it's okay if they have length 1 for now. So I'm calling them forbidden words. And I'm particularly interested in the set of words in A star, words made out of the letters of my alphabet that don't have any forbidden subwords. So I'll call that A sub F, where F is the set of forbidden words. And since 1, the empty word, doesn't have any of these forbidden subwords, this sum of all of the forbidden subwords has constant term 1, so it's invertible in this algebra. And the theorem that I'm going to talk about describes the coefficients of the reciprocal of this sum. So here's what I'm going to call theorem 1. It's actually the only theorem, but I'm going to call it theorem 1 just to have something to refer to it. If we take the sum of all of the words with no forbidden subwords, look at its reciprocal in this algebra, then the coefficients are all 0, 1, or -1. So let me look at 2 examples. So this example may look fairly trivial, but so it's not so interesting in itself, but it's a good example that shows you what's going on. So my alphabet will just be the single letter A. I'll have a single forbidden word A cubed, AAA. So it's very easy to write down the sum of all of the words with no forbidden subwords. There are only 3 of these words with no forbidden subwords, 1a and a squared. So we add them up, we get 1 plus a squared. And since there's only one letter here, even though we're in an algebra of non-commuting variables, there's only one variable, so it commutes. So we don't have to worry about non-commutativity in this computation. So we compute the reciprocal of this thing. It's 1 minus a over 1 minus a cubed, and we can expand it very easily. So we see what the coefficients are. They're 1 if n, the coefficient of a to the n is 1 if n is 0 mod 3, minus 1 if n is 1 mod 3, and 0 if n is 2 mod 3. So another example, this is a whole class of examples. Suppose that every word in F has length 2. So this is a very important special case, but on the other hand, it's much simpler than the general case. So the theorem, my theorem is not, well, it reduces to something simpler in that case. So there's a theorem of Furberg and Karlitz, Scoville, and Vaughan, who discovered it around the same time, still in the, well, in the mid 70s, that says that in this case, if every forbidden word has length 2, then the reciprocal of the sum of all the words with no forbidden subwords is just the sum of all words in which every consecutive pair is forbidden. So the way I've written it is I'm letting F bar be the complement in A cross A of F. And I'm just taking the sum of all words that don't have any of these words as subwords. In other words, every consecutive pair is in F with alternating signs. So this is actually a very useful theorem. This was kind of the main subject of my PhD thesis. And it has lots of applications, but I'm not going to talk about it because it's from the point of view of this talk, it's a little too simple. Okay. So let me talk about the Goulden-Jackson cluster theorem. And if you get anything out of this talk, even if you don't remember my theorem, this is a theorem that's worth knowing, that I think it's one of the fundamental theorems of enumerative combinatorics. So we'll suppose that the alphabet A is fixed and the set of forbidden subwords is fixed, just so that I won't need to mention them again. And I'll also assume that every forbidden word has length at least 2. So if you're forbidden, if you have a letter, a single letter that's forbidden, it's not very interesting. I mean, you can deal with that easily. So it'll make things a little easier. And I'll let little f of W for a word W to be the number of subwords of W, the number of forbidden subwords of W, counted with multiplicities. So for example, if I take my alphabet as ABC, and the forbidden words are AB and ABC, then the number of forbidden subwords of ABC is 3. It's got 2 copies of AB and 1 of ABC. And notice that it's perfectly okay to have a forbidden subword be a subword of another forbidden word. Okay, so what the cluster theorem does is it gives a formula for this generating function for all words weighted by the number of forbidden subwords. So we're summing over all words in A star. We multiply each word by T to the number of forbidden subwords. So in a certain sense, the forbidden subwords are totally forbidden because I'm allowing them here. I'm just keeping track of them. But if I want to count the words with no forbidden subwords, if I can get a formula for G of T, I just set T equals 0. And then the claim is that if I set T equals 0 here, take the reciprocal, so I get G of 0 inverse, every coefficient there is 0, 1, or minus 1. One thing I should mention is that this variable T that I'm using commutes with all of the letters. So T is part of my coefficient ring, which I'm assuming is commutative, and it commutes with the letters. Okay, so the way that we prove the cluster theorem is, rather than counting words by forbidden subwords, we count them by some of the subwords. So it turns out to be much easier to pick out some of the forbidden subwords of a word, mark them, count those things. So this will give us a formula for g of 1 plus t. So each forbidden word is either counted with a weight of t, in which it's counted, or it's not counted and it has a weight of 1. So that's the same as computing g of 1 plus t, and that's what we'll get a formula for. So I'll say that a marked word is a word in which some of the forbidden subwords are marked. An arbitrary subset of the forbidden subwords of a word are marked. So here's a picture. The alphabet is AB. The set of forbidden words is ABA, AB. And I've marked the first ABA, a second ABA, and an AB and an ABA. But there's also an AB that's not marked and an ABA that's not marked. So I don't mark, I mark whichever ones I want. And the colors of those ovals don't mean anything. That's just so that you can distinguish them. If I colored them all the same way, then it would be a little harder to tell them apart. Okay. So now what I want to do is I'll let m of t be the generating function for these marked words. In other words, I sum over all words in A star. For each word W and A star, I sum over all the ways of marking that word in this way, that I pick a subset of the forbidden subwords and I weight that by t to the number of marks. That is the number of marked subwords. So I'm going to, so m of t then is g of 1 plus t, because these, so this is actually an example of doing this, something that we do all the time in enumerative combinatorics. We count something in two different ways. I can either later, as we'll see, I'll get a direct formula for m of t by counting these marked words, but I can also count marked words by just starting with an arbitrary word, and I know all of the forbidden subwords, and I just pick some of them, which gives me the g of 1 plus t formula. Okay, so how do I count marked words? Well, I'll say that a marked word is a cluster if it can't be split without cutting through a marked subword. Or in other words, another way of thinking of it is that it consists that the markings overlap completely. So you can give a formal definition, which, you know, if I were writing a paper, which I did, I would give a more formal definition. But for a talk, we can just look at these pictures. So these are both clusters. Again, it's not a terribly interesting example, but it illustrates what's going on. So I have the underlying word AAA, 6 A's, and my forbidden subword is just AAA. Both of these are clusters. So in the second one, I've marked all of the forbidden subwords. In the first one, I've marked 3 out of the 4, but the marked words all overlap. You can't cut this anywhere without cutting through one of the marked words. But here's something that's not a cluster. So every letter is in a forbidden subword, but I can cut it right in the middle. I could cut it right there. And these don't overlap. So that's not a cluster. So the key fact is that every marked word can be decomposed uniquely as a concatenation of clusters and single letters. So here's a picture that shows this decomposition. Here's a marked word. You just cut it wherever you can cut it without cutting through one of these ovals. Okay, and now I'll define the cluster polynomial of a word just to be it's the generating polynomial for the clusters whose underlying word is W. So I take my word, I look at all of the possible clusters on it, and for each one, I put a weight of t to the number of marked subwords, and I add those up. And the decomposition of marked words into clusters and letters tells us that the generating function, m of t, for marked words is given by this formula. So every every marked word is a sequence consisting of letters, which are here, and clusters, and the clusters are counted here. So all I have to do to get my theorem is I just set t equals -1 in this cluster polynomial, and hopefully I'll get 0, 1, or -1. That's all I have to do. So, okay, so, but in particular, I do want to write down the cluster theorem because it has a lot of other applications. If I replace t by t-1, I get what I call g of t. So the generating function for all words by the number of forbidden subwords is given by this formula. So as I said, this is actually useful. You can compute this in a lot of cases. So this is the cluster theorem. And it's worth mentioning that if you want, you can assign different weights to different forbidden subwords. Because I'm going to set t equals 0 in this formula. This is general enough for my application, but you can give the forbidden words different weights. Okay, so to prove theorem 1, all I have to do is show that when I set t equals 0 up here, I get 0 or plus or -1. And that's the same thing as saying that this cluster polynomial evaluated at -1 is always 0, 1, or -1. So how do we prove that? Well, we're going to get a recurrence for the cluster polynomial from which it'll follow. So first, things will be easier if I assume now that the set of forbidden words is what I'll call reduced, which is that no forbidden word is a proper subword of another forbidden word. So if I don't want to allow any forbidden words at all, then this is sufficient. So in some applications, you do want to allow a forbidden word to be a subword of another one because you want to keep track of them. You might want to keep track of the number of ABs and the number of ABBs separately. But for what I'm going to do, if I'm not allowing any of them, this is sufficient. So this will make my recurrence a little bit simpler. If in the more general case, you could do something similar, but the recurrence would be a little bit more complicated. So let's look at an example of how this recurrence works. So I'll take the word A, B, C, D, E, F, G. Here I'm taking a word with all distinct letters, just so that when I talk about subwords, if I say the subword B, C, D, you know exactly where it is. So I'll take my forbidden words to be A, B, C, well, that list, which you see right up there, a bunch of consecutive subwords here. And we want to compute the cluster polynomial for A, B, C, D, E, F, G. So first, let's look at all of the forbidden subwords in W. And here's a picture that shows all of them. There are 1, 2, 3, 4 of them. So we want to get a cluster. That means we have to take some of them that overlap and cover everything. So one observation is that any cluster is going to have to contain, so we're going to look at these from right to left. G has to be in one of the forbidden subwords, and it's in only the last one, EFG. So any cluster has to contain EFG. And it also has to overlap when we move from right to left, it has to overlap with the next one moving to the left. So it's got to overlap with either the green forbidden word or the blue ones. Those are the only two that the orange oval overlaps with. So if it contains the if CDE, CDEF is also one of the marked words, then this thing ends, it ends like this. And if CDEF is not marked, then CDE, the blue oval, has to be a marked word. So we have two cases in which the last parts look like this or like this. And then if we're in this case, if you sort of forget about the, remove the G and remove the orange oval, what you have to have left is a cluster on A, B, C, D, E, F, which automatically has to contain this green marked word. Or in the other case, you'll have to have a cluster on A, B, C, D, E, and that'll automatically contain this blue marked word. So we get two cases, and then it's easy. The marked words that are counted here are counted by the cluster polynomial for A, B, C, D, E, F. And then we'll have a factor of t for this last marked word. And the same thing here, we'll have the cluster polynomial for A, B, C, D, E, and then another factor of t for this last marked word. So what we get is this recurrence that the cluster polynomial for W is t times the cluster polynomials for these two shorter words. So the same thing works in general. Well, we can iterate this and get formulas for the cluster polynomials of these smaller words. So if you look at what you get in the general case, you're going to get a recurrence. And I don't need the exact details. It's going to be of this form that if you sort of look at these things from the smallest to the largest, you're going to start off with a cluster polynomial for a single forbidden word, which is going to be t. And then you're going to get cluster polynomials for larger words, all of them starting at the beginning and ending at some marked word. P sub k is going to be t times this sum of the previous values of these p's. And the last one for sum m, p sub m is going to be the cluster polynomial that we're interested in. So what I want to do is then set t equals -1, and we get this recurrence. It's just setting t equals -1 here. And what I claim is that when you have a recurrence, a sequence that satisfies a recurrence of this sort, all of the entries, all the values of the p sub k are 0, 1, or -1. And this was actually proved by Greene in, well, a kind of a related result, which I'll talk about in a little while. The proof is very easy. To prove this, you have to prove something slightly more general, which you can prove by induction. Well, of course, it'll have to be a proof by induction. But the slightly stronger statement is that the entries, the non-zero entries, are alternately -1, 1, -1. So the fact that they're alternating, the non-zero entries are alternating, is what allows you to prove this by induction. And I'll just give an example that makes it clear why this happens. So suppose that my sequence starts off -1, 1, 0, -1, 0, and so on. And so then what we're going to do to get the next term, we're going to add some final subsequence. So starting somewhere, we're going to add all of the terms from there to the end. And we can ignore the zeros. We're just adding alternately -1s and 1s. And either they're the same number of -1s as 1s, in which case the sum is 0, or there's one more than the other. And since we're always, our sum is always going to end here, the last non-zero, if there are any non-zero terms in our sum, the last non-zero term will be a 1. And that means that the sum, if it's not 0, the sum has to be 1. And because we have this minus sign, the next term of my sequence will be -1. So in this case, whatever this r sub k is, r sub k tells you where you're starting the sum. The sum will either be 0 or -1. Okay, so that proves Greene's lemma, and this completes the proof of theorem 1, just in case you lost track of where we were. So I want to talk now a little bit about Curtis-Greene's theorem, why he was looking at this. So he proved another theorem about things that are 0, 1, or -1. Looks, well, somewhat different. So he's looking at a lattice generated. You take a set of intervals. Well, he just said it's in the integers, but it could be in any totally ordered set. Take a set of intervals and take the lattice of all unions of any of these intervals ordered by inclusion, including the empty set. So this is going to be a lattice, and Curtis-Greene proved that the Möbius functions, all of the Möbius functions of this lattice are -1, 0, or 1. It turns out that it's enough to, it's enough to prove it in the case where X is the bottom element, which is the empty set, and Y is the top element, which is what I'm going to talk about. So the reason why, or the connection between Curtis-Greene's theorem and my theorem 1 is that these Möbius function values are in fact cluster polynomials evaluated at -1. So they have to be 0, 1, or -1. So let's see why that is. I'll do this by an example rather than trying to give any kind of formal proof. So let's take the word A, B, C, D, E with forbidden words A, B, C, B, C, D, and C, D, E. So they're marked here, all of the forbidden subwords, sorry. And let's look at the clusters. So there are two clusters. We have to have A, B, C, and C, D, E as marked words to have a cluster. And we could, for B, C, D, we could either have it or not have it. So there are two clusters. The cluster polynomial is t squared plus t cubed, and evaluating it at t equals -1 gives 0. So I'm now going to construct a corresponding lattice of the type that Curtis was looking at. So to get the intervals, what I do, it may not be quite obvious that this is what you should do, but if you think about it, this is what works. So I'm going to take the sets. What I really want is the positions of the letters, but just to make things easier, I'll use the letters instead of their positions. So I'll take, for each forbidden subword, I take the set of corresponding letters, but I leave out the last one. So for the forbidden word ABC, I take the set AB, and for the forbidden word BCD, I take BC, and for CDE, I take CD, and I look at the lattice of unions of these things. And here's a picture of the lattice. And for those of you who are familiar with Möbius functions, you can probably compute the Möbius function of this pretty easily, and you'll see that you get 0, the Möbius function from the bottom to the top. The connection with clusters is given by a well-known formula for the Möbius function. It's one of my favorite formulas for the Möbius function. It doesn't seem to be as well-known as I think it should be, although it is pretty well-known. And this is a formula that actually explains the connection between Möbius inversion and inclusion-exclusion. So it says that in a lattice, the Möbius function from 0 to 1 is the sum over all sets of atoms with join 1 of -1 to the number of elements of that set. And the connection with clusters is that these sets of atoms are exactly the positions of the letters that correspond to clusters. So this sum in terms of the cluster polynomial, it's exactly the cluster polynomial evaluated at -1. And so that's why it has to be 0, 1, or -1. And that recurrence, what I called Curtis-Greene's lemma, is what Greene used in his paper. He got a very similar recurrence for this Möbius function and used that lemma. Okay, so when I submitted my paper, I got 2 referee reports back, and one referee said, "Oh, this is a great paper," And the other referee said, oh, this is pretty good, but you should look at this paper of Dotsenko and Khoroshkin. So I looked at the paper of Dotsenko and Khoroshkin, and I found that they had proved a similar theorem. They did not use the cluster theorem, so it was a different method, but they did have something which was very similar to my theorem 1, and they could have proved my theorem 1 if they had wanted to, but they were only interested in words without repeated letters, and they weren't interested in non-commuting generating functions. So they didn't state my theorem 1, but their proof would have worked for it. And they were, what they did is they used, based on some earlier work of David Annick quite a while ago, they gave a kind of explicit, somewhat more explicit than I had, description of what this coefficient is, whether it's 0, 1, or -1. So if you look at what I did, I mean, I have this recurrence. You can tell it's 0, 1, or -1, but it's hard to say exactly what it is. So their characterization, it was still recursive, but it was a little more explicit than mine. And so I went back. I have to say, they, well, I'll say that later. Okay, so I looked again at the recurrence, and if you, the fact that in this recurrence, the terms are always 0, 1, or -1, that's true no matter what the RKs are, as long as RK is between 1 and K -1. But if we use the condition that the set of forbidden words is reduced, we have an additional condition, which is R sub K -1 is less than or equal to R sub K. And it turns out that this implies that in my sum, at most 2 of the summands are non-zero. So this was a little bit surprising. It didn't seem to be obvious. I mean, once you know that this is true, it's not hard to prove. You can prove it by induction. But I don't think I would have thought of it myself, although if I had done more examples, I probably would have. And what this says, and of course, if none of the summands are 0, then the sum is 0. And if 2 of the summands are 0, they have to have opposite signs. So this sum is 0. So the next term is 0 also. And that means that P sub K is non-zero if and only if exactly one of these is non-zero. And so this gives you a more explicit way of describing when you have a non-zero coefficient. And so I can, to make this a little bit, to restate this in terms of the words, I'll say that a word of length 2 is salient if its coefficient is plus or minus 1 in this sum that I'm interested in. So from what I just said about the recurrence, we get that W is salient if and only if either it's a forbidden subword, in which case this coefficient is going to be 1, or it ends with a forbidden word that overlaps with exactly one shorter initial salient subword. So from what I said on the previous slide, it can only intersect, it has to intersect with either 0, 1, or 2 previous salient words. So it's salient if and only if it overlaps with exactly one of them. And so this isn't still not totally, I mean, you might hope that there was something even more explicit than this, but this is probably the best that you can get. So here's an example. Suppose that, my favorite example, the alphabet is just A and the forbidden word is just A cubed. And we want to know, is A to the 6th salient? So we look at the shorter initial subwords of A cubed that end with A cubed. What will determine which of them left to right. So the first place where we have a forbidden subword is AAA, and that's a forbidden word, so that's salient. We look at the next one, which is AAA, just moved one over. That overlaps with just one salient word, so it's salient. And the next forbidden word is the next AAA. that overlaps with two salient words. So it's not salient. So that has a coefficient of 0. And then the next one, it overlaps with two previous forbidden words, but only one of them is salient. So this is salient. So we get the same coefficients as we had before. And you see this pattern of 1 minus 1, 0, 1 minus 1, 0, and so on. Okay. So, and the signs start off 1, minus 1, 1, and so on. The reason why this is starting with a 1 rather than a minus 1 is that coefficient in the reciprocal is the negative of the value of the cluster polynomial. And I think this is pretty much all that I have to say. So I'm going to end with a real anticlimax, which for completeness, I have to say that another proof of my theorem 1. So I looked at this paper of Dotsenko, and then I contacted Dotsenko, and he gave me some additional references to this work. And one of them was this paper by lyudu and Vlassopoulos, which it actually did state explicitly my theorem 1 and gave another proof, which I have to say I didn't understand. So all of these other people are working on more algebraic things. And so it has something to do with homologies of, well, monomial operads. It is related to, if you take this algebra of formal power series and non-commuting variables, if you just mod out by the forbidden subwords, then you get a quotient algebra. And they're studying this algebra from the point of view of algebra. I mean, you can sort of see that counting the monomials that are left is the same as computing the Hilbert function or the Hilbert series of this algebra, which is what they're doing. But I don't actually know what the connection with homology is, but it's all connected with the mechanic and so on. And so this is all I have to say. So again, I'd like to congratulate Ian and David for a great career is still ongoing, and thank the organizers again. Thank you.
The questions? Yep.
Yeah. Oh, well, it's really, you know, if you're looking at consecutive patterns and permutations, well, so one thing you could say is that that's exactly what this is. I mean, in permutation patterns, people are perhaps more likely to be interested in actual permutations, where instead of an arbitrary word, you just have a permutation of 1 up to n, so you don't allow any repetitions. But it's very easy to go from words to permutations. I mean, it depends on exactly what kind of generating function you have and what kind of information you have, but you just throw away the things that have repetitions and then you get permutations.
So I'll just repeat the question was that,
Oh,
yeah, what's the
sorry.
connection between this and the permutation patterns?
Yeah.
Yeah.
Thanks.
Other questions? Yeah.
Okay, from the patterns of size 2, you have only silent words, is that right?
You only have what?
Silent.
Salient. Yeah, so in the case where every forbidden word, so the question is in the case in which the forbidden words all have length 2, is every word that has a cluster on it is salient. Yes. So more precisely, in the case where every forbidden word has length 2, the clusters are very simple. If you have a word which is every cluster polynomial is just a single binomial. There's only one cluster on a word in which you have to have every consecutive pair is marked. There's no choice. So the cluster polynomials in that case are not very interesting. You never have the, I mean, you only have zeros when there are no clusters. Yes. Yeah, in that case, it's much more explicit. Yes. There's no cancellation, in other words. no cancellation in that case.
Other questions? Yep.
So when you were talking about first there,
Yes.
you said that the sum of the mobile function is the same as sum over clusters. I don't understand why it's using clusters. Why can't you just perfectly partition interval? Wouldn't you join still be the whole thing?
Okay, so the question, I'm not sure I can restate it. So the question is about Curtis-Greene's theorem and the connection between the clusters and the
Why it had to be clusters?
why it had to be clusters. Oh, okay. So that's related to why I had to cut off the last letter of every forbidden word. So in fact, what happens is another way of describing clusters is, so to each marked word, you associate, let's say, the interval of where it occurs. And then a set of positions will correspond to a cluster if and only if when you chop off the rightmost part of each interval, the union of those things gives you everything. So that's why it sort of takes away the overlapping, put it back, they have to overlap. So that corresponds to the union being the whole thing. So I hope that explains it.
Any other questions? Yep.
Yeah.
Could you somehow make the proof work without
Probably, but the thing is, if you're not allowing any forbidden subwords, let's say if I forbid AB and ABB, I don't need to forbid ABB because I could just, if I don't allow AB as a subword, I can't possibly have ABB as a subword. So probably the proof would work without that assumption, but it would just be a longer proof of the same thing. It wouldn't prove anything more general. I don't know. I kind of, my feeling is that it probably wouldn't give you anything. It would just give you a slightly longer proof that considers, more cases. So you can certainly write down a recurrence for the cluster polynomial. In that case, you'd have to consider the case that the word ends with two different forbidden subwords. And so you'd have more terms in your recurrence. But we know from this argument that when you set t equals -1, the extra terms would cancel out. So because the cluster polynomial at t equals -1 is going to have to be the same whether you have these forbidden words included in other forbidden words or not.
So yeah, that question was about whether there was interesting post-set combinatorics if you didn't forbid forbidden words that included the others. Maybe time for one more question if there is one more. No? Okay, well, we'll thank the speaker again.